All right, so now on to our next topic. So I'm going to talk now about a concept called validity. This is a concept that does not exist in RTL languages. So validity is the notion of when values of signals are meaningful. Okay, so we saw in the exercise that you just did with the calculator that we had a calculator that was doing something meaningful every other cycle. Okay, and so on alternate cycles, the gates are there, the gates are doing something, they're driving a value, but that value has no meaning. And validity gives us a way to convey that. So here I'm taking the Pythagorean theorem computation and I'm applying validity. So we have our Pythagorean theorem circuit. It's capable of computing distance for us in the broader context of the circuit where we're using this computation. Some cycles we may be using it, some cycles we're not. Often in hardware, 90% or more of the time, our circuit's just sitting there idle, not doing anything. But it's burning power, and we want to save power. So this concept of validity tells us when, in this circuit, when we're performing a Pythagorean theorem computation. So in the code here, I've created a valid signal, and I've assigned that signal in stage 1 at the beginning of my pipeline. And then I've applied that valid as a when condition. This question mark valid is the condition under which this computation is meaningful. And that condition applies to every stage of the pipeline. So under that condition, we've got the computation. And this code results in a waveform depicted here. The red values would be referred to as don't care values. So these are the values under which the condition is false. In this code I haven't provided the expression for valid, but in the waveform where you see red, that would correspond to invalids. And then you can see the computations when it's valid. So a number of benefits from doing this. You can see, for one, in the waveform is much easier to interpret. Instead of being a sea of values, you can clearly see the values that have meaning, and you can very clearly see the pipeline nature of the computation. So debug is much easier. Your design is just generally cleaner because you have information about the modeling that you didn't have, you wouldn't have in an RTL setting. And it also results in better error checking. So the approach with the conditions today is to the compilation tool, so Redwood EDA Sandpiper tool, is going to produce RTL that injects don't care values when the computation is not meaningful. So most simulators are capable of modeling zeros and ones, and also don't care state, meaning it could be 0, could be 1, I don't know, and I don't care. Actually, you can sort of distinguish between I don't know and I don't care, but in any case, the term we use is don't care. And generally, simulators also support so don't care would be referred to as X. They generally support a Z state as well, high impedance value, which would be basically an undriven net. So in this case, the waveform we're looking at, the reds are reflecting these don't cares in simulation, which have been injected from the knowledge of validity. These don't cares are what's giving us better error checking. So the simulation is going to propagate these don't care values. If you have a don't care at the input of a gate, that don't care is going to generally show up at the output of the gate as well. And so if your logic is inadvertently consuming something that you didn't intend to consume, that was an invalid signal, that's going to propagate through your logic. You're going to end up seeing don't cares in simulation where you didn't expect to. That's going to result in throwing assertions and whatnot. So you can catch logic that's inadvertently consuming signals that it shouldn't be using this mechanism. And then the last benefit is something called clock gating. So let me now introduce clock gating. So clock gating is a power savings feature. A lot of the power consumption of your circuit comes from the clock. Okay, so that, you know, this global clock is oscillating, transitioning twice per cycle, and those transitions have to be driven throughout your chip. That burns a lot of power. And with a notion of when signals are holding something meaningful, we can use that notion to know when we need the clock. Right? So if a value in the circuit is meaningless, there's no reason to drive a flop provide a clock pulse to a flop that's going to carry that value through the flip-flop. It's garbage. The output of the flip-flop can be anything in that case. So we don't need a clock pulse. So we can use this notion of validity to condition off the clock pulse when we don't need it. When we know that the input to the flip-flop is garbage, we condition off the pulse for the clock. So these little blue boxes here you see that are basically knocking off the teeth of the clock. These are clock gators. And the clock gating condition is the when condition associated with the signal that we're driving through the flip-flop. And often, you know, in circuits, a lot of time the logic is not doing anything meaningful, and we can save a significant amount of power this way. Okay, and with TL Verilog, you know, you can generally, when you're modeling clock gating logic, it tends to be an afterthought when you're using an RTL methodology. But in TL Verilog, you want that notion of validity from the start. It's helpful for development and debug, and then you can have your clock gating in there from the start, which is a big benefit.